Design your own life. With Dimas Satya.
Subscribe, tekan tombol bel, share dan like videonya ya guys. Terima kasih.
What is the universe really made of? What is truly fundamental in the reality that we perceive? In 400 BC, Greek philosopher Democritus came up with the idea of atoms as being fundamental. He believed that these were solid pieces of matter which could not be divided any further. 2,300 years later, in 1897, J.J. Thomson discovered something smaller than an atom, called the electron. And in 1912, Ernest Rutherford discovered that atoms had nuclei. Then we found that nuclei were composed of protons and neutrons. These were thought to be the fundamental components that all things are made of until the 1960s, when we found that neutrons and protons were composed of even smaller things called quarks. Two kinds, up quarks and down quarks. Today, everything that you can see around you is thought to be made up of just these three particles: electrons, up quarks, and down quarks. That's what all atoms are made of. Your phone, your desk, your skin, your grass, everything. At least, this is what most people are taught in science class. The only problem is, it's not true. And physicists have known this for decades. These particles are really not fundamental. The best theory in physics tells us that there really are no particles at all. Nature is made of fields. Reality is fundamentally many different fields. These things we call particles are merely waves in the field. So what in the heck are these fields, and what do they tell us about the nature of reality? The idea of particles, even the particles that I've talked about numerous times composing the standard model, is not what the universe is actually made of. The particles are fiction. The fundamental nature of the universe are not particles, but fields. These are fluid-like substances that can be perturbed, they can vibrate and experience excitations. What exactly are fields? Mathematically, a field is something that takes a value at every point in space. They're not really made of anything other than that from a strictly physicist point of view. Think of it this way. If you have a fireplace in a room, the temperature at every point in that room would have a value. This would be a field of temperature. This is analogous to the universe's fundamental fields. And these fields in nature are everywhere. You can't escape it. If you take a strong metal box and remove everything from it, all the gases, all the atoms, all the photons, what will be left in that box? This is what we think of as a vacuum, like the vacuum of empty space. But in fact, this vacuum is alive with fields, and they're constantly moving and changing. The Heisenberg uncertainty principle means that a quantum field cannot sit still. Instead, they're moving and vibrating and changing their value over time. This is a computer simulation of empty space. All the bubbles that you see popping and bursting are perturbations of empty space. Particles are constantly being created and destroyed in this emptiness. But these particles are really excitations of fields that pervade all of space. What you can see in the world around you are excitations of these fields. In fact, all you can see is really only the excitations of four of the fields. You can see photons or light, which are vibrations in the electromagnetic field. Electrons are vibrations in the electron field. Up quarks and down quarks make up the protons and neutrons in the nucleus of all atoms. They are vibrations in the up quark field and down quark field, respectively. Amazingly, everything that you can see around you, your phone, your desk, flowers and trees, the earth below your feet, everything is composed of just these four fields. But there are more than just these four fields. In fact, everything that we designated as particles in the standard model, the best theory of physics we have, are really excitations or vibrations of their own fields. The total number of fields would be 17, including the Higgs field. Note that space-time itself is thought to be a field, but so far has not been able to be incorporated in quantum field theory. It would be the 18th field. All the so-called particles are really waves. And when I say wave, I don't mean a wave like an ocean wave. The 2D models are just a visual aid, but the waves would actually be three-dimensional. Can you see any of these fields? Not really, but you can kind of get an idea by putting a magnet together with some metal filings. The lines that you see are really the magnetic field lines changing due to the magnet. Another way to visualize fields is to imagine the volume of the universe being filled with water, as if we were living in an ocean. Now imagine that instead of water, the ocean is filled with multiple fluids, about 17 different kinds of fluids, and these fluids are of different colors. This may look really spectacular and weird, but this is somewhat analogous to what our universe actually looks like, except that you cannot see these fields. Why is this theory better than the idea of particles? The key thing that this field eliminates is the idea of action at a distance. So for example, in Newtonian gravity, you have to concede that the gravity of the sun somehow affects the Earth, which is 120 million kilometers away. How can something affect something else so far away without touching it? This is action at a distance. Even Newton thought that action at a distance was absurd. He said, "It is inconceivable that inanimate, brute matter should, without the mediation of something else, which is not material, operate upon and affect other matter without mutual contact." Einstein's theory of general relativity eliminated the idea of action at a distance by replacing space with something called space-time, which is a field that pervades all of reality. And he showed mathematically that gravity is really due to a bending of this field of space. Whatever happens anywhere to a particle in space is governed by what is happening in the field near the particle. In order for something to propagate over distances, it has to affect its field locally, then propagate from the local point to another distant point, then affect the field locally at that distant point. This is similar to the way a wave will propagate in water if you throw a rock in it. Fields have the property that they can give their vibrations or energy away. If you strike the field hard enough, they will affect other fields. So in this decay, the energy of the quark field of the neutron can be transferred to the quark fields of the proton, plus electron field and antineutrino fields. In addition, particles and antiparticles are excitations in the same field. They're just described as equal and opposite excitations of the field. This is represented by two opposing waves. When these waves come together, they annihilate each other. You are affected by these fields every day. When you call someone on your cell phone, you're putting excitations in the field and affecting the electronics within the cell phone of the person you're calling. This is action at a distance in practice, except it's not action at a distance. Your cell phone is creating excitations in the electromagnetic field that is propagating from you to the cell tower and eventually onto the receiver on the other end. The combining of field theory with quantum mechanics is called quantum field theory, or QFT. So essentially, all the excitations of fields happen only in chunks of energy. The energy of the wave is determined by the mass of the particle. What is a mass? A mass of a particle is just the energy needed to vibrate its field. Energy, if you recall, is equivalent to mass using Einstein's famous equation, E equals mc squared. The field will simply not accept energies below a certain threshold. Once you tap the field hard enough, however, a particle is created. This discrete unit of energy that the field can accept is what we call the rest mass energy of the particle in a field. It is the fundamental amount of energy that must be added to the field in order to create a particle. So for example, one electron is created when an electron field is excited by 0.511 mega electron volts, which is the mass of one electron. If you add energy equivalent to 0.4 mega electron volts, no particle gets created. If you put in 1.1 mega electron volts, then 2 electrons get created, and so on. This works for all the particles. All the electrons in your body and my body are waves in the same underlying field. The field is fundamental. The electrons are not. Also present in this room and your room are the up quark field and the down quark field. And all the atoms in your body are composed of particles which are ripples in these three fields. It's the same field that you, I, and everyone on Earth is in. In fact, it's the same field that all the other planets and the sun is in. We are basically composed of ripples in the same three fields everywhere in the universe. Now, there's no indication that ripples in my field can communicate with the ripples in your field, but it's one continuous field and everything is connected to it. Fields don't tell us everything though. It does not tell us what dark matter is, what dark energy is, or how the Big Bang occurred, or why there is more matter than antimatter in the universe. So there's still work to be done. Now, how are waves in the field related to the probability waves of quantum mechanics and the Schrödinger equation? When we say that an electron is a particle with a position and velocity, this is wrong. And it's not because we can't measure its position and velocity. It's because there's no such thing as a position and velocity. All there is a wave function. It is spread all throughout space, and it only tells us what the position and velocity will be if we choose to measure it. So for example, the shape of the electromagnetic field is the wave function of photons. The shape of the electric field is the wave function of electrons, and so forth. The wave function is what really exists. And when you observe the electron, you don't see the wave function because the wave function has collapsed into a discrete value. This can be predicted by Schrödinger's equation. The fields are vibrating and modulating, but when you measure them, they resolve into individual packets of energy called particles. So quantum mechanics says that fundamentally, reality is different when you measure it versus when you don't. Every particle in the universe is a tiny ripple in the underlying field, molded into a particle by the machinery of quantum mechanics. The quantum fields vibrating at every location in space and throughout time are the fundamental building blocks of nature. So the age-old question of whether light is a particle or wave can be answered. They are waves. A particle is just what manifests when we measure the wave. Who discovered fields? It should be noted that Michael Faraday came up with the idea and actually used the word field in his notebook in 1845. Are fields a real thing, or are they just mathematical constructs? Even though a field is made of no substance, fields are considered real physical stuff. This is because they exist in space and have energy. In addition, their properties can be calculated and accurately predicted by experimental results. Now we get back to the question, are these fields fundamental? Well, I think it's fundamental in the sense that it is the limit of our understanding. But it could very well be that these fields are just an approximation of a deeper level of reality. Because ultimately there should be some fundamental reason why these fields have the properties that they do. Why does the electron field have a minimum requirement of 0.511 megaelectron volts? Why does it obey mathematical rules? Will we ever know the answer? Unlike many physicists, I think we will. We may not even be asking the right questions. And I think the answer will come when we humans know enough to ask the right question.